Welcome to the course on FPGA based signal processing systems. Today we will be looking at the technology review in detail. So the technology review can be classified into three parts, like the age of invention and the expansion and also the accumulation age. After that we have the current age which is going on, and what about the future of this FPGA technology review. So in case of this that age of invention, the period which is covered in that invention was 84 to 91. The first FPGA which we had looked at into the previous lecture is the Xilinx XC2064 with 64 logic blocks and 3 input LUTs, also register which is approximately 1000 gates. So now if the technology used, the process technology used was this 2.5 micron technology. So the size of the device, the die size was large in that case. So the mainly the functions which needs to be fit into that large die was the challenge. So the programmability, as we discussed that in the previous lecture, there were three categories with the SRAM, antifuse and the flash one. So in the invention age, the preferable ones were this SRAM based was also available, where the programmed device, when if there is a reset or power off, the program will go off. So in that case, whenever you switch it on, so you have to reprogram it, whereas in the case of the antifuse, it is only one time programming. Also we had looked into the other part, like that flash devices, that when you program it, it retains it over throughout. So the Actel comes up with that in that antifuse technology in that, and both were part of the invention age, SRAM based and the antifuse one. So the cost containment was the critical issue, that the die size was large, and so it is high, the cost is high, and the yield issues were also there, and the cost containment was the main problem in that case. So the cost per function of the die size were very important in that case. They were trying to reduce this cost per function in that along with that die size. So if we move on to this invention age, what are the architectural inventions are taken place in the case of FPGAs? So the lookup tables was in the generic FPGA architecture. We have seen that the lookup tables were part of it. That logic blocks contains these lookup tables, and these lookup tables initially were this I said in the first FPGA it was 3 input LUTs, and then later the Xilinx in that age has introduced these 4 input LUTs, which is considered to be the coarse grained, so that the complex logic blocks were there, and because of that, many the LUTs, the unused LUTs were also part of this in this age. So the configurations, not all the LUTs were used for configuring a particular function or the functionality, the design which they were using in that time. So the fixed functions were also preferable because of saving the space, the area. The unused LUT configurations needed to be reduced, so they've gone for this finer grained architectures. That is also an invention in that were introduced to reduce the logic cell waste, especially the unused LUTs and then logic cells. Well, so these were for fixed functions. So that should be kept in mind, that these were fixed functions, not the functions which were any of the functions. So the finer grained were specific to the functions, and the technology were also introduced. The programming technology, the antifuse was also used, because the antifuse used a single transistor ones, that Actel's single transistor antifuse technology were used, and the SRAM demanded the 6 transistor cells. And also if you see that this based FPGAs having even the power goes off, the program which was deployed in the FPGA also goes off. So we need to reprogram it. Of course there is a provision to reprogram it, and when the power goes off, to avoid that reprogramming, again the people were using the PROM devices, programmable read-only memories, as a second die attached with the SRAM cells. So that demanded actually the 6 transistor cells. So the second die was again the area expansion of the FPGAs. So these things in the demanded also, it enabled this larger capacity. So the Actel came up with in 1990 Actel 1280, the larger capacity FPGAs with anti-fuse technology. So that was the invention during invention age. So the other part of the architecture of the FPGA was this interconnect. So what are the changes made in this interconnect? Actually, there were the logic blocks were placed in the array, and there was a need of close connections of the logic blocks. That is, the people were working for the very efficient small FPGAs those times. So in that case, the pass transistor based connections were found to be efficient instead of long wires, that is the slow wire. So when you have the long wire interconnect wires in the architecture, that means that there is a delay in the process. So in the connection generally. So the unused wires were found, and they're very strict in this interconnects. So the interconnect area was also reduced, and saving in area, and the efficient FPGA was the design was the first choice in those duration. And then the interconnect area was efficient. Also, the area is reduced, and if we overall look at the age of invention, so there were challenges. So apart from these architectural ones, that logic blocks and the programmability concerns, also the interconnects, so the short wires especially, and these FPGAs were very small, and the problems were also be small in that case. So there were in order to implement certain systems, like there were multiple FPGAs, partitioning of this FPGAs, smaller FPGAs, many smaller FPGAs were used. So instead of partitioning one FPGA, so there were multiple FPGA blocks, FPGA systems have been integrated to implement a particular system, because the FPGAs were small in size. And then the placement and routing. So because of the small in size, that logic blocks, they were manually routed, and even the placement and routing was done manual. The automation was not thought of in that duration. So it was not an essential one. The automated placement and routing process of, that means choosing this logic blocks and the interconnects, was not automated in that age of invention. So if area efficiency was the main concern, and the people in the architectures and the short wire things were being the priority in the invention age. So the design tools, the ASICs had this application specific ICs had the universal software to handle the design, whereas in the FPGA's case is that during this invention period, there is no universal FPGA design tool. So because of the different architecture, so how to unify these architecture, how to make the software design tool which can make the automated placement and routing for different architectures, that was a real challenge during that time. So the manual design, due to small device and limited EDA tools, were the challenges, and so the EDA development were initiated at that time. So it was not in full form, or it is not established, the design tools were not established. Now what we have in this era, that the EDAs were not the part of the invention age. So if, coming to the continuing with this challenges again, this cost sensitivity. So if the die size was a primary concern, so the die size, if it is 5% increase in die size, also causes the double the cost. So the yield due to the investment on these FPGAs were less in that case. So the cost reducing the cost was also the part of this invention age. So cost sensitivity was a challenge in that time. So reprogrammability, as I said, that the SRAM FPGAs required external PROMs, that is allowed for the second die, as I said, an FPGA, and then because when the power goes off, they want to retain the program. So in that case, they want to program it using this PROM as an external PROM. So it was also not a valued one in the reprogrammable part as the age of invention. So the interconnect limitations, so we have the shortest routes, like the sparse routing made designs difficult to implement. In the sense, shortest routes were preferred, and so if there is no shortest route available, there will be routing sparsity. So the sparsity in the design was the design was it was difficult to implement the all design in this. So these were the challenges of the age invention. So taking the invention age, the main concern was the area efficient FPGAs, which were small in size and shorter routes. Also the die size was the concern, and because of the cost effectiveness. So and the antifuse technology was a little bit in higher side than the SRAM technology, because of the PROM demand in the SRAM based FPGAs. So in those years, in the age of invention, if you see, also the ASICs were also part of it. So what 1980s, that what are the, when we compare this FPGA and ASIC, so see that this application specific ICs are this having the readily available built-in order ASICs were available. In that case, the custom mask was required, and they buy the custom mask with the cost that is called the NRE, that is non-recurring engineering cost, and then they add the units to it. The custom mask, his initial cost was large in case of ASIC, and so the fabrication times were also longer, and the high risk of errors in recovering for this costly the silicon respins were also used in this ASICs. So ASIC as a whole, so if we compare it with FPGAs cost wise, this is NRE is coming into picture. So whereas in case of FPGAs, there is no NRE cost, and that is non-recurring engineering cost, or no custom masks of the cost which is involved in that. So then across all the customers, this is leveled up in the NRE cost in case of FPGAs. So and FPGAs were instantly available, that compared to the ASICs, and it has the self emulation. The verification phase was very good for the FPGAs. So in case of ASICs, they have to do lot of simulation to verify the functionality of the device. So whereas in case of this FPGAs, they had the self emulation. So just download the program and check the outputs, that is the verification. Download and try that. That would be the emulation part. So it was very useful in the self emulation was very useful in the case of FPGAs in 1980s, and it reduced the most of the verification in comparing to the ASICs during that age. Also, there is a crossover point. If we consider this FPGA is more cheaper when we have the low volumes, that is number of units are less. When we buy the units of less numbers, then it was cheaper. But ASICs, which are suitable for the better units, or for the more volume devices. So if we take the units versus the cost, so we can say this is number of units, and here is the total cost for this device, to understand what is the crossover point. So the NREs, actually the ASIC had this point of this type of a curve, which is the initial cost, I can say. So this is the initial cost involved in the device, which we take it as ASIC, that is application specific ICs, which needs non-recurring engineering, that is a custom mask need to be bought. So whereas in case of the FPGAs, it's a linear curve anyway. So it is, this is the FPGA, and this curve, the slope of this curve is little flat, and it is here. We can say this is the curve of the ASIC, and there is a crossover point, which is comparing to the slope of this ASIC, and the FPGA had a higher slope, and both of them match at a particular point, and this is the curve which y-axis which is extending, and the number of units, that is, suppose we take it as a nth generation units. So for a particular unit, yes, there is a cost involved in this ASIC, and if it is growing, or I can say that here, as the units, addition of units, the multiple units increases, compared to this NRE cost, the additional units will be very less. But when we buy and when we add the FPGA device, initially the FPGA devices, the number of units, for number of units it is less, and if we add more and more FPGA units to buy, so and then it would cross at a point definitely. Okay, this is called the crossover point. And though the initial units were higher cost, and when we come to a particular point, units in this case both crosses, so the lower volumes, so if you consider this part of the device, the FPGAs are lesser cost, having the lesser cost. That is why it is cheaper for the number of units are less the FPGA, but it is not so with the ASIC devices. When this point is trying to move, and if we take the another generation, so if you take the next generation, or the ones which could be taken as further, in this also we can see this ASICs having the some of the other costs, that the NRE will be little higher in this case, and there will be a crossover, so that will be higher than this crossover, of course, I'm sorry, and higher crossovers here, that is for the next generation. So this point will be keep on moving higher and higher as the generation increases. So for one generation the crossover point is somewhere, and the lower volume of FPGAs are lesser in price, and after the crossover point there is not much difference between these two. So the higher units, the ASICs would be better. So if you want the bulk volume of devices, then ASIC would be better after the crossover points. For cheaper ones, that is the FPGA cost would be better. So the crossover point, what we mean is here these 2 points. It depends on the generation. So the for nth generation, and then n plus 1th generation, and then it moves on to the next generation, and so on. So this is about the ASIC and FPGA in 1980s. Basically the cost one, total cost, and the initial cost which is involved. And although the ASICs had that case of high risk errors, and because it needs this silicon respinning, and the fabrication times also higher, whereas the self emulation was the good characterization of this FPGA for verification. So in 1980s, again this programmable array logics were also popular during this time when FPGAs came up. These are 2-level logic structures. So this architecture is having only AND OR arrays. They have the number of inputs and its inverts. So in that, those things have been taken in the AND array to get the minterms using this AND array, and then there were fixed OR arrays. So these fixed OR arrays are used for implementing the logic. So digital logic. So PALs were very popular devices, and there were dedicated softwares for implementing that as well. But there is the problem with the PAL was the growth. So if you have the number of inputs more and arrays are required, and the scalability was limited in that case. So the quadratic growth, if it is the number of inputs square and arrays are required, in that case if there is number of inputs are more, and then the growth will be quadratic, and the device size again will be more, and it is there is a limitation in this scalability. Also this, once the design is large, so again the power consumption is a problem. So high power consumptions were the disadvantages of this PALs. And when we consider these FPGAs in that duration, so we had seen this in the previous lecture, that the generic architecture has the memories LUTs, or the logic blocks, which are the distributed configuration, this memory cells. So that is the greatest advantage in the FPGAs, and this is scalable according to the Moore's law. So the Moore's law is whereas the PALs were failing to do in the scalability, where the FPGAs were more adapting to the scalability. So according to the Moore's law, the rapid growth or the phase of the Moore's law, the FPGAs were very much suitable or adapting to the Moore's law transistor sizing. and the shorter the interconnects. So the in 1980s, as the interconnects, the shortest routes or the routing wells, short interconnects were preferable to reduce the area, the programmability area needs to be reduced. So that improved the scalability also in case of FPGAs. So in comparison, if we take this PALs and this two-level logic structure, which is the AND or arrays, the FPGAs have completely eliminated this AND array the architecture of PAL and um, took over the place of PALs, and there is a great replacement of PALs the PALs with FPGAs. So because of this interconnects and the logic blocks, which are memory cells, and with easy adaptability of the FPGAs to the Moore's law and so on. So this is about age invention. In that age of invention, so the efficient, smaller size, shorter interconnects were preferable compared to ASICs. The cost, NRE cost, is not involved in the FPGAs. Also, the AND arrays of the PALs were completely eliminated by FPGAs during that time. So if we come to the age of expansion. Okay, so the age of expansion, that is the next period of this in the FPGA developments. Or so 1992 to 99, if we take these 8 years of space, that there were again the Moore's law as pressurized to do this FPGAs. There is a change in the FPGA development. That means that there are the quantitative changes of the Moore's law, which has made large or qualitative changes in the FPGAs which are built using the semiconductor technology. So during that time, when the the leading technology were not available to the FPGA architects, or so they instead of going for the invention age, that they were focusing on more on expansion of this developed FPGAs. So the expansion, which means that more LUTs, adding the more logic blocks or more gates, was that the LUTs were growing in the FPGAs during this period. So that's why this is expansion. So one is the LUT growth, that is the capacity growth from the 10,000 gates of this invention age actually to the 1,000,000 gates. We can see that XE4010 to the vertex XE 1000 as 1,000,000 gates, where the larger FPGAs were available in this duration. So the more logic blocks and complex blocks also. So this is one expansion which has happened in this age of expansion. And the interconnects, so as the LUTs were growing, there were increase in interconnect wire length also. So people were not bothered about the wastage of area of programmability. That was the concern in the age of invention. But wire length, the interconnect wire length was more, that is keep on increasing. That these were the capacity growth and interconnect wire length growth were the main contributions of this expansion age. And the process advancements in the process technology, they were even including this chemical mechanical polishing, that is CMP enabled, that enabled the FPGAs with more metal layers instead of only the scaling with transistors. So it had the more metal layers as well. The process advancement in that age is also the CMP was one to be worth mentioning. In the same age, again the concerns were not only the area, still the area matters, as in the case of age of invention, but the area, there will be a trade-off between this area performance. So the area can be compromised if performance is better, and the features can be added more, so that the area can be compromised. Also the ease of use, how we can connect the logic blocks efficiently. So those were the real concerns during the expansion period. So instead of the architectural innovations. So the cases, because of the larger size FPGAs in the expansion age, so there is a need for there was actually the need for automation. So the automation, due to the increased FPGA complexity and the manual design or routing which were practice in the case of invention, age of invention. So now it becomes impractical because of the larger size in FPGAs and the complexity. So there were the need for the automated synthesis. If you have the HDL, then synthesis process needs to be automated, placement and then routing, these were become essential part of this. So how we can automate the total design process. So that was the concern. So the tools related to that, they were trying to the EDA tools which were just initiated in the invention age had become more established and developed ones during the expansion age. So the FPGA vendors developed proprietary EDA tools. So the life of FPGA was completely depending on the EDA tools. That means how efficient your EDA tool is, so that the synthesis, placement and routing were done efficiently. And still the area was concerned. The area was also a concern in this case. So there is a trade-off. So larger designs were there. So because of this, and then the reduced design time, the design automation tools made the design time less, and also the improved reliability on the design. So by the EDA tools also. So there is a rise in the demand of this design tools. So after that, in the expansion age, there was advancements as well. So these advancements were long wire segmentation. So if we use the EDA tools or the design automation tools, the placement and the routing, so we don't bother about this the small short connections are the concerns. So here is the longer. It's okay if we just properly automate the design. So the wire spanning between the multiple blocks also allowed. The wastage of interconnects was not a problem at all. So the improved performance was the main concern during this period. So the interconnect advancements have taken place. The multiple blocks have been connected automated with the wire spanning, and so there is an reduced need for this precise placement. So it is also not a concern, and so the ease of using automation is the easy use was the main concern in this expansion age. So using the automation, so the trade-off was cost of wasted metal. It was acceptable in that during that time. That is okay if some portion of this FPGA's architecture is wasted, that is okay, and that is compromised, and the result is that simplified placement, routing and better performance was the result of the interconnect advancements. So if you take to this expansion age, again with the major concerns like SRAM as a technology of choice. So in that expansion age, SRAM has dominated. So we see that it has an advantage of compared to the anti-fuse and flash devices. So when the Moore's law had pressurized this process technology, the process nodes were the only switching to the next process node was the only choice for the FPGA vendors. So in that case, that the architects, what they did is the SRAMs were quickly adapted to the new processing nodes. Whereas in the anti-fuse case, it was the problem that it was not adapting to the new processing nodes. So the SRAM technology has grown, or it has the system programmability and field updates were easier in the case of SRAM devices. So anti-fuse limitations were the slower to qualify on new nodes. That means that the one-time programmability required, that ASIC like verification. So the ASIC verification was very cumbersome in case of ASIC, so the more simulation and other things. So because of this one-time programmability, there is a lot of verification needs to be done if we use this anti-fuse FPGAs. So because of the advantages of this SRAM, that is, which was not in the case of age of invention, in the expansion age, the SRAM based FPGAs have dominated because of the Moore's law advancement. The capacity to be increased twice, and then the cost should be reduced to half. So that phase of Moore's law advancement pressurized this switching to new process nodes, that process technologies, and which were easily adapted by SRAM based FPGAs compared to the anti-fuse one. So the anti-fuse demanded that it is slower to qualify those new nodes. It was very difficult to make these anti-fuse ones. So the SRAM FPGAs were dominating during that time. but the antifuse ones and the flash ones were not, I mean, these are relegated in this case of in this age of expansion. So this is about the expansion age. Still we have the major details about this LUT as a logic cell of choice, also how this LUTs become the logic cell in the expansion age. So what are the major concerns about this is because even the ease of synthesis tools to map the arbitrary functions were the main reasons in the expansion age. So any arbitrary functions can be implemented with the LUTs. That is also a choice in the expansion age. And reduced interconnect needs also, the unused LUTs have been nullified in this case. So the many LUTs have been used. So the inefficiency is reduced by the logic cell. This logic cells, it has been chosen as a logic cells. So the efficiency, because LUTs are like a memory blocks and it can be easily laid down on the silicon, so it is more efficient. And the Xilinx adapted LUT based architecture, even Altera also adapted to this LUT based architecture. So the expansion age LUT based architectures were popular. In all the for all the vendors have gone for this LUT based architectures. So coming to the expansion age, so the Moore's law, the challenges were this: the Moore's law led to the increased capacity of FPGAs, that is larger FPGAs, and it demanded automation. The design of automation tools were essential in this part, that it is not only initiated, it has grown, and the full life of FPGAs depending on this automation design tools. Also longer interconnect segmentations were possible. Also the efficient architecture, because of that the invention age, some invention age architectures, efficient architectures could not be automated in this expansion age. So they disappeared in that some area efficient architectures. The SRAM devices exploited new process technology which dominated the expansion era. So thank you.